Hi grade teens, today we'll be going through magnetic fields. I am following the Solutions for All textbook. We are doing page 196 to 197, the theory is on those pages. We're also following the exam guidelines, page 12 and 13. If you look over here, page 12, magnetism is over there. There are definitions that you need to know. There are also, each bullet point is a checklist of things that you should be able to do by the time it comes to tests and exams. So, when we look at magnetic fields, we can break this up into two. We can look at magnetic or magnetism, and we can look at fields. Okay, what is a field around an object? What does that word mean to us? So, when we look at magnets, we have two categories of magnets. Firstly, we have permanent magnets, and there are three elements that are permanent magnets. So those are iron, nickel, and cobalt. When we look at a permanent magnet, the sections within, or the pieces within a magnet, all of those magnetic domains line up and point from one end to the other. So you can see that all of those arrows in each domain are aligned. They are pointing in the same direction. When we look at things, the other type of magnets, they are called temporary magnets. They are made by aligning those different magnetic domains. So you will see in a temporary magnet, the domains are unaligned. They are not aligned. How we turn that piece of metal, whatever it is, into a magnet is to align the magnetic domains. So basically what you do there is, if the substance is magnetic, it is a permanent magnet. Within here you would have your magnetic domains being aligned. If that is moved over something that is a temporary magnet constantly, these magnetic domains would start shifting and everything would become aligned. That would turn the substance into a temporary magnet. Over time, and when it is not in the presence of other magnets, it would revert to being an unaligned object. Right, the other part, magnets, of magnetic fields that we can look at are magnetic fields. So a field is an area around a magnet in which another magnet will be able to feel the force of that magnet. So if we go to our examination guideline, it says, where are we? A magnetic field is a region in space where magnet or ferromagnetic material will experience a force. It is a non-contact force. Now, non-contact means they can act over a distance. So two magnets can act over a distance. They do not have to be making contact with each other. They can act over a distance. So the first point is that they are non-contact. The second point is that they are invisible. Now that may be a no-brainer, but if you have ever played with two magnets or tried to put a magnet onto a fridge, you cannot see the field around the magnet or around the fridge, but you can feel the effect of the force between the magnet and the fridge door, for example. The next point, and this point is explained in homework activity or homework exercise 1 on page 203, and it's question 10. It's quite a long exam type question dealing with graphs. This is really important because it lays out the mathematical relationship between force and distance. What you need to know for exams is that force is inversely proportional to distance. So the force, the strength of attraction or repulsion, increases the closer they are together. Automatically, if you have any experience with magnets, you will know that already. The closer, when you have two strong magnets, the closer you try and get them, the harder it is to get them close. Whereas if you have magnets that are further away from each other, there's not as much attraction or repulsion. So our mathematical relationship there is force is inversely proportional to distance, and that means distance. Okay, then the last little bit that we need to do on this sheet is drawing field lines. There are 3 rules with drawing field lines around a bar magnet. First, we have the closer the field lines are, the stronger the force that is experienced. So around the ends, the poles of the magnets, the force is the strongest. Whereas around the equator, you can see that the field lines are further apart from each other. The magnetic field that is experienced is weakest. The arrows must always point from the north end around the outside towards the south end. Again, it's not a circle around. From the north end, around the outside towards the south. So that is the way that your arrows point. So arrows point from north to south around the outside. The last thing you need to remember here is that field lines never cross each other. You will see that each of these meet at a point, but they do not cross each other at any point. I am going through the basic rules, notation, and magnetic interactions of the magnetic fields. I'm covering page 198 in the Solutions for All textbook. So our basic rules, like with positive and negative charges, our like poles repel and our opposite poles attract. So for an example over there, like poles would be a north pole and a north pole. So 2 magnets where they both have north poles pointing towards each other, they would repel each other. Whereas a force of attraction would be seen between a south pole and a north pole. So different poles pointing towards each other, you would see a force of attraction between the two. When we look at bar magnets, often one end is one color and the other end is a different color. When we are looking at that notation, the science notates it as red. The red end of a magnet is north, and the blue end of a magnet is south. Right, then we have looked at the magnetic field around a bar magnet. However, what you need to know is the interactions between the magnetic fields. So what you would see is that you know that a magnetic field goes from north to south. So you would not expect it to move around that way. You would expect the north pole to be attracted directly to the south. So over here, your magnetic field lines always go from north to south. Over here, it would be further away, so you'd start seeing a curve. Over here, you would start seeing a rounded magnetic field, but this end of the magnet is not only attracted towards that south end, it is also attracted towards this south end. So you would start seeing a north to south interaction this way as well. Likewise, at the bottom, you would see a north to south interaction as well. So we know force is inversely proportional to distance. Therefore, the further away they are from each other, the weaker the force. So out here, the force of attraction or repulsion is weaker, whereas where the field lines are closer shows that the force of attraction is much more strong. Likewise, over here, we know that the south end is attracted to the north. However, we do not say that the south goes up and the arrow points that way. That would be incorrect. We know that magnetic fields go from north to south. And likewise, this end is attracted from north to south. When they start getting very far away from each other, this end is also, you can't see that nicely, it's actually also attracted down to that end, and likewise that end, the north end of there, is attracted to that south end. So you can see that this is a whole system where every north is attracted to every south, and likewise. Also, something to remember is that this is a 3D magnetic interaction. It is not only on the y and x axis, it is also happening out towards you. Okay, north to south, around in a 3D formation. When we start looking at unlike poles, you will see that the north to north, that interaction will not be happening. The magnetic fields will be deflected as soon as possible. So the magnetic fields here will not interact with each other. They will be attracted from north. They will be repelled. So you will not have any of those parallel lines. They will be repelled as quickly as possible, flattening the magnetic field within that space and moving towards the south. Remember, our annotation there is always from north outside towards south, so you will see your arrows always moving along the outside, north to south and north towards the south pole around the outside of the magnet.